Okay, that should be working. So you'll get the standard type of question, some antiderivatives questions there. I think for the class test, there's 5, 2 marks each. So I'll just give you the function, you give me the antiderivative. Next week, I'll give you a more detailed scope, but that's roughly how the section will be. And then after that, we're going to look at the applications of antiderivatives to physics. And then that will be another 5-mark question. Okay. So let's start with the simple ones, just finding the antiderivatives. So number 1, we have f of x is equal to sine 3x plus 2 cos 2x. Okay, so you're given the function. We want to find the antiderivative. Now we know that we can do it for each part of the function with that sum and difference rule. And also any constants in front of the function, we can just take that out of the antiderivative. So here, this 2 doesn't affect our working at all. Okay, so the first one, sine. We ignore the inside part. We'll get to that later. What's the antiderivative for sine? Negative cos. And then the 3, if we were doing the derivative, we times by 3. Antiderivative, we divide by 3. It's always the opposite. Okay, and then the next one, again, we ignore the 2, right? Constants in front, we don't worry about. The antiderivative for cos, sine, good. And then we've got a 2 on the inside, so we need to divide by 2. And then plus c, very good. Okay. So again, in the test, this will be like 2 marks, right? So antiderivative for this one, antiderivative for this one, that gives you your 2. Forget your plus c minus 1. Okay. And we'll see in the follow-up question why this plus c is so important. Okay. Number 2. F of x equals cos squared x. Okay. Now again, we look at our table. We see there's cos, there's sine, there's no cos squared. So we're going to have to do a little bit of work before finding the antiderivative. But we know that for all of these trig functions, there's a whole lot of those trig identities we can use. So for cos squared, the one we're going to use is that double angle identity. So cos squared we can write as 1/2 1 plus cos 2x. Okay, remember last time we looked at sine squared. That was 1/2 1 minus. So the sine squared comes with the minus, the cos squared comes with the plus. Okay. Now here we can expand this out. So this is just going to be 1/2 plus 1/2 cos 2x. Now we can just do it term by term. So let's find the antiderivative for this. Okay, so the half, that just becomes half x. Yeah. Okay, then the next one, forget about the half, forget about the 2. The antiderivative for cos, sine. Good. And then here we've got a 2, so we divide by 2. And then plus c. Okay. Again, something like this, 2 marks, trig identity, final answer. Okay, they'll all be around 2 marks. Okay, number 3. Okay, f of x is equal to x squared minus 3x plus 1 all over x. Now we know that the antiderivatives only have 2 rules. The sum difference rule, the constant multiple rule. There is no quotient rule. Okay, so given a quotient like this, you cannot write down an antiderivative, right? Nothing we can do. So instead, we're going to split this fraction over this denominator. So we're going to have x squared over the denominator, 3x over the denominator, 1 over the denominator, and do it individually. Again, there's no quotient rule, so we have to do it individually. So x squared over x, that gives us x. Minus 3x over x, that's just minus 3. And 1 over x, just 1 over x. Okay. Now we've got individual terms, and we can do the antiderivative for each. Okay, first one, x. Okay, there's an invisible 1 in the exponent there. Add 1 to the exponent to make it 2. Divide by 2, half x squared. Okay, and then the 3, it just becomes 3x. That's easy. Okay, and then the 1 over x. Remember, that was the exception to the power rule. This is x to the minus 1. But if we add 1, we get 0. We can't divide by 0. So we can't use that. So this was the exception where this becomes natural log. Yeah. Remember, we did that with the inverse functions. So the derivative of the natural log is 1 over x. Antiderivative of 1 over x, natural log. It goes back and forth. Again, plus c. Okay. Any questions so far? Yeah. Easy marks. Okay. Number 4. We have f of x is equal to 1 plus x minus x squared all over root x. Yeah. Again, similar to number 3. It's a quotient. There is no quotient rule. So we're going to have to split this up like we did before. So the first one will be 1 over root x. But again, that's still not in our table. So we're going to convert that to a power. Since the root is at the bottom, it will be x to the minus half. Okay, so 2 steps in 1, we split it up. And then we know 1 over root x, that's not given in the table. So we put it as a power, because now we can work with that. Okay, x over root x, that will just be root x. Again, we can't work with that, so we write it as a power. Okay, minus, and then x squared over root x, we can think of it as x to the 4 over 2 and x to the 1 over 2. That'll be x to the 3 over 2. Okay, now each of them have their powers, so we can just do the power rule for each. Okay, first one, minus a half. We add 1 to make it a half. Divide by a half, that's the same thing as timesing by 2. So that will be 2x to the half. Okay, next one is a half. Add 1, that makes it 3 over 2. Divide by 3 over 2, that's timesing by 2/3. So plus 2/3. Okay, and you'll always see it like this. So because we're dividing, whatever fraction is here is flipped over here. Okay, because dividing by a fraction is multiplying by the reciprocal. Okay, last one. X to the 3 over 2, we add 1, that's 5 over 2, flip it over, 2/5. And plus c. Okay. Any questions with this one? Okay, so again, here we did the 2 steps in 1. So we divided the root by the denominator for each and wrote it as a power. Okay. If you want to do it in multiple steps, that's fine. But these are like 2 marks each. So if you want to do it all in one, that's fine. Okay, number 5. F of x is 2 hyperbolic cosine of 3x plus 1. Okay. Again, the 2 in front, forget about that. Okay. We just look at what the function is. Again, this inside part, forget about that. It's just the function. So the antiderivative for hyperbolic cosine is, from the table, hyperbolic sine. Good. But here we've got the 3 inside, so we divide by 3. So here the 1 doesn't do anything, because remember from the chain rule, we only look at what's in front of the x. This constant doesn't do anything. Okay, and then plus c. Okay, number 6. Okay, so we have minus sec squared 5x. Okay, again, the number in front, the -1, we ignore. The 5, we ignore. We just look at the function. So sec squared, the derivative of what gives us sec squared? Tan. The derivative of tan gives us sec squared. So the antiderivative of sec squared is tan. It goes back and forth. But not just tan, we got the minus we need to put in front. And the 5 multiplying here becomes a fifth. So this will be minus 1/5 tan 5x. And again, you can always check your answer by going backwards. So the derivative of tan is sec squared. That's good. And then the 5 jumps out in front and makes it a -1. So you can always check your answer. You know if it's right or not. Plus c. Okay. Number 7. Okay, sec x tan x. So again, remember, for antiderivatives, there's no quotient rule, there's no product rule. So if you have something looking like this, where it's a product, it must be something from the table that we've seen. So the derivative of what is sec tan? Sec, yeah. So don't be scared by the product. You think there's a product rule. No, this whole thing we know is the derivative of sec. Right, those you just need to learn. But if you've already learned the derivative table, the antiderivative table is just looking the other way. So instead of left column to right column, it's right column to left column. Okay. Number 8. F of x is 1 over 1 plus x squared. Now here we can't do any splitting, right? We've got 1 plus x squared in the bottom here. Can't write that as separate fractions. There's no quotient rule for antiderivatives. So this whole thing must be the derivative of something. That's the only possibility. So the derivative of what gives us this? Tan inverse. Yeah. So tan inverse of x, or if you want to write arctan of x, either way, same thing. And again, plus c. Okay, so please remember your inverse trig derivative. So the arctan, arccos, arcsine, arcsec, arccot, all of those ones, that should be in your table already. Okay, number 9. F of x is 1 over roots 1 minus x squared. Again, looks very complicated. There's no quotient rule, product rule, anything like that. So it must be something we've seen before with the derivatives. So the derivative of what is that? Sine inverse. Good. Yeah. So again, these ones will pop up. These ones, the one with the minus in front, that's the arc cos. If you put that absolute value of x here, that's that arc sec, right? Yeah, make sure you have those written down. Okay, last one, f of x is 3 sine x cos x. Again, we see we've got a product here, sine x times cos x, but there's no product rule, so we can't work with that. There's no function that when you do the derivative just gives us this here. Okay, so we have to try something else. We see that they are trig functions, sine and cos, so there must be some trig identity we can use to simplify this. Now, if this in front here was a 2, what identity would that be? The double angle, sine 2x. Good. So on the side here, sine 2x is 2 sine x cos x. Okay, but we don't have a 2, we have a 3, but that's fine. We can write this here as a 3. So 3 over 2 sine 2x will be 3 sine x cos x. So now the product that we didn't know what to do with now just becomes sine. We know how to work with that. So a little bit of rewriting here. So this will be 3 over 2 sine 2x. And now we can write the answer right away. Okay, so we ignore the fraction in front. The antiderivative for sine minus cos, remember the minus sign. Then there's a 2 on the inside, so we divide by 2. Again, plus c. Okay, so again, for the class test 1, was it 2 weeks' time? 2 and a bit. You'll have 5 questions like this, 2 marks each. Okay, so that will be for the antiderivative part. Yeah. Oh, something like that. Okay. Any questions for this before we move on? No. Okay. Some more complicated questions, but it's not too bad. Okay, so part 2. Okay, given that the function f passes through the points 2, 5, and the slope of the function function's tangent line is 3 minus 4x. Okay. Now be careful with this. This isn't the tangent line. This is the slope of the tangent line. Okay, so please read carefully there. Okay. Find the value of f of 1. Okay, so little word problem to do. So we've got this function f. We don't know what the function is. Okay, that's not given. But we're given 2 bits of information. Number 1, we're given a point that it passes through. So when x is 2, f of x is 5. That's given because we know it goes through that point. So we know when x is 2, from the point there, f of x must be 5. Okay, so that's from the point 2, 5. Next, we know that the slope of the function's tangent line is 3 minus 4x. Again, this 3 minus 4x is not the tangent line. It is the slope of the tangent line. So this must be f prime. Is everyone clear on that? So now, again, we've got this bit of information here. but what we want is f of 1. We don't know the function. Okay, so we don't know the function, but we do know its derivative. And now we know, how do we get from the derivative to the function? The antiderivative. If we were given the function to the derivative, it's just d by dx. If you want to go backwards to the function, it's the antiderivative. Okay, so again here, f of x to f prime of x, that's d by dx. We're given this side, we want this side, so we need the antiderivative to go backwards. Yeah. So let's do that. What will f look like? Three x, good. Yep. Plus c. Now we're going to see why this plus c is so important. The reason is because when we substitute this point here, this point needs to satisfy this equation. Let's say we got rid of that plus c. We forgot it. So I'm going to make a mistake here. We're going to rub out the plus c. Let's substitute this point, 2, 5. The left-hand side, that will be 5. Right? The right-hand side, let's substitute 2. What do we get? So that will be 6 minus 8, which is minus 2. Well, we said this was 5. That can't be right. Now let's put the plus c back and substitute 2, 5. Now if we substitute this in, we can find c such that the equation actually works. If you didn't have this plus c, you would have 5 equals minus 2. That doesn't help us. So please remember your plus c. Okay, so let's substitute now. So we're going to have the 5 there. And from before, it was the 6 minus 8, so that was a minus 2. So c must be 7. And if we take this and substitute it back, now it will work with this given point. Now we want f of 1, exactly. Okay, and finally we can find f of 1. Okay, so we just substitute 1. We get 3 minus 2 plus 7. 8. Okay. Any questions for this problem? Number 3. Find the function f such that f prime is x cubed and the line x plus y equals 0 is tangent. Yeah. Very similar to the problem before. We want the function, but we're only given the derivative and some other information. So in the previous one, we were given the derivative, and we were given some point that it passes through. Here, we are given the derivative and some information about the tangent. There always has to be this 2 bits of information that we can solve for that plus c. If we're not given the second bit of information, we would have f plus c. We don't know what that is. So we have to be given this as well. We're going to follow the same steps as before. We've got f prime. We want f. So we do the antiderivative. So f That will be 1/4 x to the 4. Again, add 1 to the exponent and divide, plus c. Okay. And again, this plus c is going to be very important because we know that this tangent line must be tangent at some point. And the way that we find that is with this plus c. And we can see that with a little picture. So on the side here, let's draw this. So we have x and y. This tangent line, x plus y equals 0. That's just another way of writing y equals minus x. So we've got this tangent line here. Okay. And we've got this function. And plus c, we don't know what that is yet. But let's say c was like 5 or something, which means we have our function shifted up by 5. So it's going to look like this. Something like that. You see that if c is 5, we're too far off the tangent line. Okay, what happens if c is like minus 2? That means we're taking our function and we're shifting it down. Well, then it might look something like this. Okay, we're shifting it down. We see that plus 5 is too much. It's above the tangent line. Minus 2, that's too small. And now it's below the tangent line. So somewhere in between, it's going to be touching the tangent line. So what we want is the special value of plus c. That will do this. Okay. Does everyone see that? You can move the function up and down. At some point, it's going to touch at just one point there. Okay, we want that value. Okay, so how can we do that? Sorry? This one?
Yeah, that one. Since it is a common point that they have.
We can do that. The only problem is we're going to have two variables because we can make them equal, the y values equal, but then we have an equation with x and c. It's two variables. What else can we do? That's a good idea. We are going to equate it to something, but not this one because there's two variables. What can we equate it to that only has one variable? F prime. Because remember, this is the tangent line. This is the gradient. We know that the tangent line has this gradient at some point, right? So we will equate the tangent line to equate the tangent line's gradient. Let's call that m, okay, from the tangent line to f prime. Because we know that with the tangent line, f prime is the gradient. We did that a while back. Okay, so what is the tangent line gradient? Well, we wrote it over here. Y equals minus x. The gradient is just minus 1. So at this point that we're interested in, the tangent line has gradient minus 1. F prime should also be minus 1. So they're the same. So at the tangent point, the derivative matches the tangent gradient. That's how we found the tangent line all those weeks ago. So f prime, that was x cubed. Well, very easy, x must be minus 1. And if x is minus 1, what will the y value be? 1, yeah. Just put in minus 1 here. So that's the tangent point, which is very similar to what we had here, where we had the function passing through some point. Now we have exactly this. We have a point. We can solve for c. Okay, so that will be minus 1, 1. And that's exactly what we needed to solve for C. Okay, so x must be minus 1, y will be 1. So C must be 3/4. Okay, so we can substitute that back, and that gives us our function f. Okay, and then again, this 3/4 that we got here, that's exactly the shift over here that we need. So plus 5, that was too much. Minus 2, that was too little. But if we shift here at 3/4, this y-intercept here, it touches at 1 point. Yeah. Any questions for this one? All good. Okay. Okay, so those were the general math type questions. Now we're going to look at more of the applications. So we'll start off with the applications to physics, and later on we'll look at applications to the chemical engineering, the electrical engineering. All of that stuff will come later. Okay, so we've got a little word problem. Okay, a particle moves in a straight line. And has acceleration a, that will be 6t plus 4 centimeters per second squared. Again, I remind you, for all of these physics applications and stuff, there's going to be units. So when we did the rates of change, we had units. When we do this, we have units. Okay. So sometimes the problems will have units, sometimes they won't. But these application problems, please remember your units. Okay, so a particle moves in a straight line, has this acceleration. Its initial velocity v at 0, so at time 0, that's the initial velocity, is minus 6 centimeters per second. And its initial initial position. Okay, so initial position, again, at t equals 0, that will be 9 centimeters. Okay, so that's the setup for the problem. We've got this particle moving. We know its acceleration. We know its initial velocity and its initial position. The goal is to find x of t. Okay. Now I'm going to put a very big warning sign before you lose 5 marks in the test. You cannot use x equals, you know, that physics thing, x0 plus v0t plus half a t squared. You know that? This will not help us, and we'll see that in a bit. As soon as you write this down, you immediately get 0 because this will not help you. Okay. Why? This formula, which we will derive in a little bit, only works for constant acceleration. Only. If acceleration is changing, this is useless, does not work anymore. We can see from this problem that a is 6t plus 4. It is not constant. Over here, this a is just a number that you put in, right? 9,8 for free fall and stuff. This will not work. Okay. So this only works for constant acceleration. Okay, so please make a note. Every year someone decides to use this formula, 5 marks gone. Okay, so please make a note. You can only use this formula for constant acceleration. And I'll explain that in a bit. We will derive this formula. Okay, so recall. Okay, so just some basic physics from last semester. You did kinematics, I think. Okay, so we have our position. What is the time derivative of position? Velocity. Yeah. So d by dt of x, that will be velocity. What's the time derivative of velocity? Acceleration. Now we've seen this before, this chain of functions. Okay, we saw it on Monday. So starting with our f, let's say, the derivative gives us f prime, derivative again, f double prime, and we can go down the chain. But what is the question asking us to do? We're given the acceleration, we want the position. So our starting point is not on the left, our starting point is on the right. We need to hop over here to get the velocity, hop again over here to get the position. How do we go from right to left? Antiderivative. So this is our starting point. We're given the acceleration. We want the velocity, so we need to do the antiderivative. And once we have the velocity, we do the antiderivative a second time, and that will give us position. So we have our starting function, we do it twice, we end up with our position. Now remember, whenever we do the antiderivative, we're going to have a plus c. So we're going to do the antiderivative the first time, and we'll get something something plus c. We do the antiderivative the second time, we get something something plus c plus d. We have two unknowns.
Plus d.
Yeah, so we did it twice. You do it the first time, you have a plus c. You do it the second time, you have a plus d. Yeah. How do we find what those are? We're going to use these initial conditions. So when t is 0, we know that the velocity must be minus 6. That will allow us to solve for the plus c from the first time. And then once we do it the second time, we'll have a plus d. But at t equals 0, it's 9. We can then solve for d. Okay. So if we have to do the antiderivative twice, we need two initial conditions because there's two variables. Okay, so with all that out of the way, let's go through the working. So we start with the acceleration from what's given there, 6t plus 4. And we just follow the same steps as before. So we want to do the antiderivative. So we don't call this like capital A like we did with the functions. We know that this is going to be the velocity. So if you just want to think about it, this is like f double prime going to f prime. Okay, so let's do that. The 6t, so there's a little 1 there, so it'll be 3t squared. Very good. Plus c. Okay, why do we need the plus c? Because it must satisfy the initial condition here. Okay, so let's write that out. So when t is 0, v must be minus 6. Okay, so let's substitute, solve for c. Okay, that was easy. T is 0, we get C is minus 6. Good. Okay, so that's the velocity. Now we need to do the antiderivative one more time, and that will give us the position. And you can think of this step as going from f prime to f. You can see the two steps we did on the left there. Okay, so we go term by term. 3t squared divided by the 3. So that will be t cubed. 2t squared. Very good. Yeah. D. Yeah, we can't call this C because we already have a C here. So we call it D. You can call it C1 and C2 if you like, but C, D, E, however many you need. Okay, now we don't know what that is, so we substitute the initial condition. Let's go back here. When t is 0, x is 9. So substitute. So it will be
2,
9. Yeah, because all of that stuff will just be 0. Good. And finally, we have our answer. X of t is t cubed plus 2t squared minus 6t plus 9. And right away, we can see why that kinematics formula here won't work. Here we've got x naught plus vt plus half at squared. You write this down, right? It's going to be t squared. But our answer here is t cubed. You can never get a t cubed from that formula with the t squared. Okay. Everyone clear with this example? All good. Okay. And now just a little side working on where this formula comes from. And like I said here, constant acceleration. So deriving the kinematics formula. So this will be a special case of what we just did, where the acceleration is constant. So we start with constant acceleration. So a of t is just some number a. Constant. Again, this is a very special case from what we did previously. And we're going to do the same two steps. We want the velocity, we want the position. So the velocity, what will that be? It'll just be at plus c. Okay, but the c is unknown. We need an initial condition. When t is 0, the velocity is v naught. Right? Yeah, v naught, initial velocity. So that means v of t is at plus v naught. You've seen that before. Okay. Now we don't want the velocity, we want the position. So we do this one more time. So this at, add 1 to the exponent, that makes it 2, divide half. V naught, that's a constant, so we just multiply by t. Plus d. Because of the antiderivative, we must add d. Now to solve for d, we use the second initial condition. When t is 0, x will be x naught. But everything with t goes away, and we're left with d. So finally, x of t is half at squared plus v naught t plus x naught. That's your kinematics equation. And you see that this only works from the very start when we had A was a constant. Okay. So this is the very special case of what we had here. Okay. With that. But this method works for any acceleration. In fact, this acceleration here doesn't even have to be linear or quadratic or anything. Let's say that the acceleration was 3 sine omega t. Right? It's not even linear, quadratic, definitely not constant. So given this, we can follow the same steps as before. So if that's the acceleration, the velocity will be, sine becomes negative cos, and then 3 divided by omega. You do it one more time, you get x. Okay. What motion will this be? Did you cover this? Hooke's law? Hooke's law.
Yeah.
The x is a sine omega t. I haven't done Hooke's law. Okay, ignore that. Okay, no, don't worry about that. You never did Hooke's law, this one. You're doing strings?
Yes.
Okay, you'll see that. Maybe we'll look at it next week then. Okay, anyway, it's the same idea. So in physics, if you have A of t from Hooke's law, which you'll see in a bit, you do the antiderivative twice, you get the position. Okay, you'll see that later on. Okay, but again, please, this is the special case. Okay, do not write this down if I give you some other non-constant acceleration. Okay. Any questions for the applications? Yeah. So in the test exams and so on, the acceleration will be some function of t. Yeah. So it will be something like this, maybe t squared, maybe that sine omega t or cos omega t like I wrote earlier. It will be some function like this. Yeah. Constant acceleration, that is for your physics stuff. Okay. We don't do that. Any other questions? No, good. Okay, so the other applications we're going to look at will be forces and potentials. You've covered that. Potential energy and forces. Okay, yeah, we'll cover that in a bit more detail later on. And then just some weekend reading. For Monday, we are going to be starting the area problem. So if you look in your textbook, this will be the last chapter under the derivative section. And then the very next section on integral calculus starts off with the area problem. Okay, that will be for Monday. Please read through that chapter. So it is the area problem for Monday. Okay, please read through that. Otherwise, you're going to be very confused. Right. Any questions? No. Okay. And then the last thing, the quiz for next week. The MCQ part of the quiz will be a bit of matching, like these questions here. So you're going to have one column with the function, one column with the various antiderivatives. You need to match them up. Yeah. So sine goes to negative cos, right? You need to match them up like that. So that will be the MCQ part. There'll be 10 questions like we did today. And then for the written part, it will be something like this, an application, or something like this. We're given a little word problem about a function. Yeah, it will be one of those two. Okay. Any questions about the quiz? You're good. Okay. See you on Monday.